Okay, now since we were talking about vector-valued functions, we can take their derivatives and integrals. And if r of t, remember t is a real number, and it gives us a vector. So we're going from the real numbers to the set of vectors. Then r prime of t is the limit as delta t goes to 0, 1 over delta t, r plus r of t plus delta t minus r of t. And when we do that, and separate r into its components f, g, and h, then this is equal to f prime of t I plus g prime of t j plus h prime of t k if f, g, and h are differentiable. It means they have derivatives. All right, and drawing a picture of this, here's a curve. Here's r. It's the origin. And if we move it over a little bit, then let's that be rt plus delta t. And by vector subtraction, this vector right here right here is r of t plus delta t minus r of t. And if we multiply that by a scalar, this vector has the same direction as this vector since they're scalar multiples. And that's right here. This is your scalar. And let me get some more colors. Okay, so I just wanted to put this in a different color. Okay, so this right here is going to be that vector. Now, as delta t goes to 0, then this vector gets closer to r of t. And what we get, let's try purple, is this purple vector right here, which is r prime of t. So that's the because you can see as we get closer and closer and closer, and that becomes r of t, then we get the tangent vector. So the tangent line to a curve C at point P is defined to be the line through P parallel to the tangent vector r prime of t. So we'll get the equation of the tangent line in a minute. Let's just do a basic example. Let's say r of t is this function ln of t I plus e to the minus 3tj plus t squared k. And I want to find the domain of r. Remember, it's the integration, it's the intersection of all the functions. Well, f is ln of t, so the domain of f, t has to be greater than 0. You can't take the natural log of a negative number or 0. G is e to the negative 3t. Well, that domain is all real numbers. And h is t squared, and its domain is all real numbers. So the intersection is 0 to infinity. So that's the domain of R. R is continuous on its domain because all the functions f, g, and h are continuous on that domain. So then we can take the derivative, and the derivative is the derivative of each component. Which is 1 over ti plus negative 3 e to the negative 3tj plus 2tk. All right, let's go through some properties of the derivative. And they're what you expect if s is a vector valued function and r is a vector valued function and you take the derivative, then you just take the derivative of each one separately when you're adding or subtracting. If you're doing scalar multiplication, where c is a scalar, then the scalar just comes out in front. So this is just like normal derivatives. If f of t is real valued, is a real valued function, remember s and r are vector valued functions. They give us vectors. F of t gives us real numbers. Then if you multiply f is real valued, s is vector valued, and take the derivative, we can use the product rule. And that's times. It's not dotted. This is a dot product. If you're dotting them, let me make that a times. You take the dot product. Again, it follows the product rule. And composition, the chain rule. If I have a real valued function inside a vector valued function and I want to take the derivative, then that's just the chain rule. And then the cross product. These are both vector valued. If I cross two vector valued functions and take their derivative, it's the same as crossing the functions and adding them. So again, that is just like the product rule. You have to watch the order there because order matters in cross product. Okay, I think we've covered it. So let's look at another example. We're going to graph these things. Let's let R of t be 2ti plus 4 minus t squared j. And then R prime is going to be 2i negative 2tj. And R of 1 is going to be the vector 2, 3. And R prime of 1 is going to be 2, negative 2. Remember, the domain is real numbers and the range are vectors. So if I sketch this, first, let's eliminate the parameter. X is 2t, y is 4 minus t squared, so x over 2 is t, and I'll substitute it back in here, and I get y equals 4 minus 1/4 x squared. So it's an upside down parabola. So at 0, I get 4, and at 1, no, at 2, I get 0. And R1 is a vector 2, 3. All right, so vector 2, 3, I go over 2 and up 3. Just a minute. That's not a point on the line. Oh, yes, it is. I'm sorry. I do this wrong. Okay. Let's see where this y is equal to 0. I have 16 equals x squared, so x is 4. So this is going to be 4 also. So it's kind of like this. So this is 0, 4. This is 4, 0. And at 2, 3, 2, 3, this is R1. And 2, negative 2 is going this way. So we have the tangent vector. Let's move it up here. And again, it should be tangent. Let me draw this better. It's going to go like that. And that's R prime of 1. Okay. And this is 0.23. It just took me a while to get that set up. Okay. A definition. A curve is smooth if R prime of t is continuous on I, an interval I. So it's smooth on I if it's continuous on that interval, and R prime of t is never 0 except maybe at the endpoints. So this just assures us that we don't have any sharp points. Remember, with regular derivatives, if the derivative is 0, you may have a sharp point. So let's try this one. And we take the derivative. All those are continuous, so R is continuous. And that's never 0 because of this 3 right here. And they're all continuous on the real numbers, so it's smooth. Now this one, we take the derivative. Those are all continuous functions. Well, R prime is continuous here, so I take the derivative, and that's continuous. Each one of those are continuous. But this is equal to 0 at t equal pi, so it's not smooth. Okay, let's look at tangent lines. Here's another example. Find the parametric equations for the tangent line to C at the point where t equal 1. Okay, so the curve C is represented by these parametric equations. So the point, if R is t cubed I plus 2t plus 1j plus t squared minus 3k, then R of 1 is 1, 3, negative 2. So the point the tangent line must go through, because that's the terminal point on that vector, so it must pass through this point. Then it's parallel to the tangent vector, and the tangent vector is 3t squared, that you just take the derivative of each one, and R prime of 1 is 3, 2, 2, so it's parallel to this vector. So the parametric equations are easy. X is 1 plus 3t, y is 3 plus 2t, and z is negative 2 plus 2t. Remember, a vector equation for a line is r0 plus t v, and it's parallel to v through the terminal point of r0. Just to review a little bit. Okay, and also, if r of t is continuous on AB, then we can integrate r of t, and that's just integrating each function separately. So if I want to integrate I'm just going to integrate this function and use fundamental theorem of calculus. I'm going to integrate 5. Let's just go ahead and integrate that. With with respect to t. And that's going to be 8i minus 10j plus 6k. Okay, look at the sample homework problems for some more examples.